Alright, hello everybody, welcome back. So today we'll be continuing my video series on Calculus 1. Today we'll be talking about the limit definition of the derivative. So our goals for today, we're talking about the limit definition of the derivative, the alternate form of the derivative, and differentiability and continuity. And next time we'll talk about basic differentiation rules. So to start off our discussion today, let's remember when we went over at the very beginning, the introduction to calculus, one of the two problems that I mentioned as being big in calculus was the tangent line problem. So let's say we draw a function, f of x. So this is our function f of x. And we want to know the slope of the line tangent to the function f of x at this point x equals c. Well, how could we figure that out? We could start by approximating with a secant. So let's say we put a second point here at x equals b. All right, so this is b, this is c. And we find the slope of this secant. Now we know here, this point is the y value at x equals c is f of c, and the y value at x equals b is f of b. So we know the slope of this line, the m secant, is equal to f of b minus f of c all over b minus c. But this isn't a very good approximation. It doesn't look too good. So how could we make it better? Well, we could slide our point B, say, to here. So this is our new x equals b. So now we draw a new secant line, and the slope of this secant line would be f of b, which is now this point here, f of b minus f of c over b minus c. So you can look at this, and we're going to make these secant lines, we want to make them closer and closer. We want to move this point b closer and closer to c. Well, as we looked at in the last video, we can look at something as it gets closer and closer and closer to a certain value by taking a limit. So what we're going to do here is we're going to take a limit. But first things first, we've got to figure out where the points are. So let's say this here is our point B, right? So let's start by saying that x equals c is c units from the x-axis. So then this point here, x equals b, is b units from the x-axis. But we want to keep making this b get closer and closer and closer and closer to the point x equals c. So that the distance between these two points, and we'll call this distance here, between x equals c and x equals d, we'll call that delta x, change in x, like the distance between the 2 points is delta x. So what we want is we want the limit as delta x approaches 0, and we know the slope formula to be delta y over delta x. So this here will give us the derivative of a function. So from this graph, we know that f, so the slope here, we need the value of the function f at point B. So we know that b minus c is equal to delta x. So if we add c to each side of this equation, we see that the point B is the point c plus delta x. And this makes sense because we said this here is c units from the x-axis. And then this b here is delta x away from c. So it would be c plus delta x. So our f of b would become f of c plus delta x minus f at c. C is still our first point, and this f of c doesn't change. Divided by, now our x value here at b is c plus delta x minus c. When we look, as you could expect, delta x is just the change in x. This c cancels and this c cancels. So we get that this is equal to the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. So this here is the limit definition of the derivative at the point x equals c. So let's work out an example. I'm going to start with a fairly intuitive one. So let's start by taking the slope of the graph y equals x plus 3 at x equals 2. So if we draw this graph here, here's our xy plane, x, y. So we know that x plus 3 looks like this. And if you look, this has a constant slope. We know from y equals mx plus b, where m here is the slope, that our slope for this graph is 1. So let's try doing this with the limit definition of the derivative. So we have the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. Now, this is a spot where I've seen some people get really confused, is that this can be a little confusing here, the f of c plus delta x. What this means is our f of x, let me change this, y to an f of x, is that f of x is equal to x plus 3. If you wanted to know, say, f of 2, you would plug in 2 where x is in this function. So this is 2 plus 3. Say you wanted to know f of c, you'd plug in c for x. It would be c plus 3. Now, let's say you wanted to know f of c plus delta x. You would just plug in c plus delta x for where there's any x in this function. So f of c plus delta x would be c plus delta x plus 3. So we're going to plug this in up here. So this becomes the limit as delta x approaches 0 of f of c plus delta x is c plus delta x plus 3 c plus delta x plus 3 minus f of c. We plug c in. We get c plus 3 all over delta x. Now, in this case, we know that our c value, the value where we're trying to find the derivative, is x equals 2. So let me just erase these c's, or those where I will put a 2. Now, we see here that if we were to plug in 0 and try direct substitution with this limit, we get 2 plus 0 plus 3, which is 5, minus 2 plus 3 is 5, so that would give us 0. And then divided by delta x, which gives us 0. So that's an indeterminate form. We need to keep going in order to find the limit. Now, often when working with the limit definition of the derivative, you see we have this delta x on the bottom. We want to be able to get the numerator to a point where we have a delta x that we can factor out to cancel the delta x on the denominator. So in this case, let's keep doing algebra with the numerator and see if we can get a delta x to cancel. So we have the limit as delta x approaches 0. Now 2 plus 3 is 5. Of 5 plus delta x minus 2 plus 3 is 5 over delta x. And this is the limit equal to the limit as delta x approaches 0. And we can see here that the positive 5 and the negative 5 cancel. So this gives us the limit as x approaches 0 of delta x over delta x. Now these delta x's cancel, and they give us limit as delta x approaches 0 of 1, which is equal to 1. So this is the slope of the graph f of x is equal to x plus 3 at x equals 2. That's the slope of the tangent line. Now, the neat thing is the slope of the tangent line at any given point on a function is the same as the slope of that function at that point. So if we have a function here, let's call this one g of x. And we know at this point here, the slope of the tangent line is, let's say 3. We know that at this point, the slope of this graph is 3. So now let's say we wanted to know the slope of the graph, the slope of the curve of x squared plus 1 at x equals 2. This one's a little more difficult because we have an x squared, but let's try to work it out. So again, if you want to try to work it out by yourself, feel free to pause the video at any point and then come back when you have the answer, or if you get stuck, and I'll go over it. So we have our function here. F of x equals x squared plus 1. And we're looking for the slope of the line tangent at x equals 2. So we're going to start with the limit definition of the derivative. Limit as delta x approaches 0 of f of c plus delta x minus f of c over delta x is equal to f prime at c. And this f prime of c is how we denote, or rather, f prime of x evaluated at x equals c. This is how we denote the derivative of f of x evaluated at x equals c. Though oftentimes people shorthand it and say f prime of c. So if you see f prime of c, often what that means is f prime of x evaluated at x equals c. But we know that f prime of x at x equals c is equal to the limit as delta x approaches 0. Now, what is f of c plus delta x? So we know our c is 2. So if I erase these 2's here, or the c's here and the c here, we get our new, we get the limit definition of the derivative at the point x equals 2 to be f of 2 plus delta x minus f of 2 over delta x. So f of 2 plus delta x, we plug in 2 plus delta x here, and we get 2 plus delta x squared plus 1 minus, and now we plug in 2 and get 2 squared plus 1 all over delta x. And let's move this around algebraically. Let's start by squaring this. So we know that if we have a plus b squared is equal to a squared plus 2ab plus b squared. So in this case, our a is 2. So we get this is the limit delta x approaches 0 of 2 squared plus 2 times delta x, which is 4 delta x plus delta x squared plus 1 minus 2 squared plus 1 over delta x. We have a positive 2 squared here and a positive 1 here. So this here is 2 squared plus 1, and we subtract 2 squared plus 1 from the numerator, so these can all cancel out. And this simplifies down into the limit as delta x approaches 0 of 4 delta x plus delta x squared over delta x. Now we can factor a delta x out to the front. We get the limit as delta x approaches 0 of delta x times 4 plus delta x over delta x. And these delta x's cancel, so we get that this is equal to the limit is delta x approaches 0 of 4 plus delta x, which is equal to 4 plus, we know we're taking the limit as delta x approaches 0, so we can directly substitute 0 in for delta x. So that gives us 4 plus 0, which is equal to 4. So we know that the slope of the graph of x squared plus 1 and the slope of its tangent line at x equals 2 is 4. Now let's say we wanted to take this calculation one step further, and we wanted to calculate the equation for the tangent line at x equals 4. So we know from the point slope formula that y minus y1 is equal to m times x minus x1. So we need to know the point x, y, and we need to know the slope m of the graph of f of x at x equals 2. We've already figured out the slope, so we know m equals 4. And we know that x equals 2, so we have 2 here. And our y value is just going to be f of 2. So first step, we need to calculate f of 2. F of 2 is just 2 squared plus 1, which which is equal to 4 plus 1, which is equal to 5. So we know that our point is 2, 5. X equals 2, y equals 5. So now we plug these values here into this equation, and we get y minus 5 is equal to 4 times x minus 2. We distribute the 4 out, and we add the 5 to each side. We get y is equal to 4 times x minus 4 times 2 is 8 plus 5. Y is equal to 4x minus 3. And this is the equation for the line tangent to f of x at x equals 2. That is 4x minus 3. Now let's say we wanted to find a function for the derivative at a point. Or instead of having to calculate the derivative at every point, let's say we wanted to know the derivative of f of x at x equals 3. We'd have to go through this calculation again to figure out what the slope ends up being. We can generalize the limit definition of the derivative at a point in this way. So let's say we have a graph. This graph is f of x. We said we had a point x equals c, and we had another point placed at c plus delta x. So we have that the limit as delta x approaches 0 of f of c plus delta x minus f of c over delta x is the derivative of f of x at x equals c. But we don't want to necessarily calculate it at a specific point c. We just want to know what the derivative is going to be for any given x. So how we can do this is say, instead of saying that this specifically is x equals c, set this as x. And then this here becomes x, and this here is just x units away from the x-axis. So we could do it over for this point here as well. We could have this point be x. And we could have x plus delta x over here. So this spacing once again is delta x, meaning the point here is x equals x, or the x value here is our original x plus our delta x. We can rewrite this equation to become the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And this is equal to f prime of x. This will give us the antiderivative function, or this will give us the derivative function, sorry, not the antiderivative function. That'll come later when I talk about integrals. But this will give us the derivative function. And it'll give you a function of x, meaning let's try it out for this problem over here. So we want to find f prime of x. We know that to be the limit is delta x approaches 0 of f of x plus delta x minus f of x over delta x. So this becomes the limit as delta x approaches 0 and f of x plus delta x. Now this one is even trickier because we have an x here, we have an x here. But remember, what we do is we just plug in whatever's in here into whatever our x is here. So we see inside of the function, we're looking for the f of x plus delta x. So this is what's inside the function. So we just plug this in here, where x is. So we end up with limit as x approaches 0 of x plus delta x squared plus 1 minus f prime, or minus, and then this here, f of x, sorry, I confused myself there, went into autopilot. This here, f of x, is just x squared plus 1. So minus x squared plus 1 all over delta x. So this becomes the limit as delta x approaches 0. And now this, we need to square this. So it's x plus delta x times x plus delta x. So we can FOIL this out. We get x times x is x squared. X times delta x is x delta x. This x times delta x is x delta x. And then these delta x times delta x is delta x squared. So we get that this is x squared plus 2x delta x, where these two add together to make 2x delta x, plus delta x squared plus 1 minus x squared plus 1, well, x squared plus 1 minus x squared plus 1. These cancel out. And of course, this is all over delta x. So this becomes the limit as delta x approaches 0 of 2x delta x plus delta x squared over delta x. We can factor a delta x out to the front and cancel. And I'm going to just, we have a delta x here, delta x here, delta x here. I'm going to cancel one of these. So we get, this is the limit, is delta x approaches 0 of 2x plus delta x. And we can directly substitute the 0 in for delta x. And that gives us, this is equal to 2x plus 0, which is equal to 2x. So we know now that if f of x is equal to x squared plus 1, f prime of x, or the derivative of x, the function of the slope of x, of f of x, at any given x, is equal to 2x. Now, we know that f prime of x evaluated at x equals 2 should be 4, because we calculated that earlier. Now, we can plug the 2 into this derivative function. So f prime of x evaluated at x equals 2 is equal to 2 times 2, which is equal to 4. But let's say I still wanted to calculate the derivative of f of x at x equals 3. Well, I can use the same function, f prime of x evaluated at x equals 3 is equal to 2 times now x equals 3, which is equal to 6. So that's the limit definition of the derivative. Let's go through another example of the limit definition of the derivative. This one's going to be a little tougher because it involves rationalization, but shouldn't be too bad. So, let's say we want to find f prime of x given that f of x is equal to the square root of x. So if we want to draw this on a graph, we see that this function looks something like this. I'm going to just pick a point x as my representative point. X, here's the tangent line. And what we want to find is we want to find the derivative function. We want to find f prime of x. So we know that f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. We know f of x is square root of x. So, as delta x approaches 0. So f of x plus delta x will be the square root of x plus delta x minus f of x is just square root of x divided by delta x. Last time when I was talking about the limits, I talked about rationalizing. Or what you can do is you can multiply the numerator by square root of x plus delta x plus square root of x. And what that'll do is you multiply this, and this just gives you x plus delta x. This would give you minus square root of x plus delta x, but this would give you plus square root of x plus delta x. So those terms cancel, and these terms here give you negative minus x. But you can't just multiply the numerator, because this wouldn't be an equivalent function. But if you multiply anything by 1, it's the same thing. Like if I have 1 times n cubed plus 6, it spits out is n cubed plus 6, right? But let's say I had 2 over 2 times n cubed plus 6. Well, 2 over 2 is just 1. Or 2 plus n divided by 2 plus n times n cubed plus 6. 2 over n, or 2 plus n over 2 plus n is just equal to 1. So anything divided by itself is equal to 1. So we can also multiply the denominator by square root of x plus delta x plus square root of x. And what this is doing is multiplying the entire function by 1, but it's giving us a form of it that's easier to deal with. So this gives us the limit as delta x approaches 0 of x plus delta x minus x, and that's because these middle terms cancel out, and square root of x, negative square root of x times positive square root of x would be negative square root of x squared, which is negative x, and then positive square root of x plus delta x times positive square root of x plus delta x would eliminate the square root. And then this is divided by delta x times this. We have this on the denominator, square root of x plus delta x plus square root of x. Now we look in the numerator, the x and the negative x cancel out, leaving us with just a delta x in the numerator. But the delta x in the numerator and the denominator will cancel out, and this leaves us with the limit delta x approaches 0, sorry, that's hard to read, my chalk is running a little low, of 1 over square root of x plus delta x plus square root of x. Now we can directly substitute 0 in for delta x. We get 1 over square root of x plus 0 plus square root of x, which is equal to 1 over the square root of x, because x plus 0 is just x, plus square root of x, which is equal to 1 over 2 square root of x. So f prime of x is equal to 1 over 2 square root of x. So this is the derivative of this function. Let's say I wanted to know what f prime of -1 was. Well, let's look at the graph. If you look at the graph, it's bounded from 0 to infinity. But so the domain of this graph is 0 to infinity. If we want to find its slope at x equals -1, the function f of x doesn't exist in the real world at x equals -1. Let me just so what's the slope here? It doesn't exist. Since the function itself doesn't exist, the slope of the function doesn't exist. So that brings up some rules for differentiability. First one, if a function f of x is not continuous at x equals c, then it's not differentiable at x equals c. Say, for instance, we had a graph here, and this is f of x. And let's say this is x equals c. We know that the limit is f of x, or as x approaches c of f of x exists. This is the limit. But what's the slope at this point? Well, the function isn't defined here, and it's not continuous there. So it doesn't have a slope there because there's no point there for it. Like if we wanted to test the point x equals c as our base point, the point doesn't exist. So we can't have a tangent line going through that point, meaning it doesn't have a slope at that point. And another case is the derivative doesn't exist if the derivative from the left and the derivative from the right aren't the same. Now that sounds kind of odd at first, but let me draw the graph f of x is equal to absolute value of x. So you look at this, and this here is f of x. So you know that the slope from the left side, m here, equals -1. Because on the negative side, this is basically the function f of x equals -x, which has a slope -1. From the right side, the slope equals 1. So what's the slope at x equals 0? Well, is it -1? Or is it 1? Is it neither? Well, the slope here, there is no slope at that point. I mean, what would the tangent line look like? Like, would it look like this? 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 Probably, definitely wouldn't be that last one. And let me illustrate this by drawing the graph here of f prime of x. So this is f So we know that the slope, which is f prime of x, from 0 to infinity is 1. We know that the slope from 0 to negative infinity is negative 1. Well, what is this? What is the slope at x equals 0? And as you can see, it doesn't exist. The slope is not defined at x equals 0. And what this tells us is that anytime you see a graph that has either a point or that has one of these, and the reason the derivative doesn't exist here is you look from this side, the slope is approaching negative infinity, and from this side, the slope is approaching positive infinity. So when you have anything like this, the derivative doesn't exist. Or when you have any kind of discontinuity, the derivative also doesn't exist at that point. Now, if we wanted to calculate the derivative, say, at this point, we could, because it's a continuous function. And this is another important point, is since a function is required to be continuous in order to be differentiable, right, as we've already established, meaning if a function is differentiable at x equals c, then it must be continuous at x equals c. Therefore, differentiability implies continuity. So that's it for today. Next time, we'll be talking about basic differentiation rules. So I'll go over the power rule, the constant rule, the derivative of x at least. I might decide to go over more. We'll see. If you have any questions on anything, leave them in the comments below. Hope you enjoyed. Hope the video helped. And have a good rest of your day.